the recording. We're going to talk about something called implicit differentiation. Okay, this is section 3.5 actually. Okay, good discussion, by the way. I appreciate your showing interest in what I did my research on. And you know, many of you are getting ready to move that direction, right? You're taking Calculus 1. It's the window into a bigger world. Okay, so we all love circles. We all love circles, and what I want to do is I want to find the equation of a tangent line to this circle. The circle is x squared plus y squared equals 25. So I want to find an equation of the tangent line to that circle at the point 3, 4. Now 3, 4 is on the circle, of course, because 3 squared plus 4 squared equals 25. This circle, what's the center of the circle? The circle x squared plus y squared equals 25. The center is the origin, and that's right, Nicholas, that's right, John. And what's the radius? What's the radius? That's right, Nicholas, the radius is 5. Okay, so basically what we have here, and I'll draw, I got a picture on the next page, but you know, we have a circle here. Okay, we have a circle centered at the origin with radius 5. Okay, there's the origin right there. And the point 3, 4 is on the circle. Okay, and we're interested in finding an equation of that tangent line. So again, here now we're presented with the issue. I mean, if I want to find the equation of the tangent line, I need to find the equation of a tangent line, I need to find what do we need to find? Got to find the slope. And finding the slope is exactly, that's right, it's the same as finding the derivative. So I need to find dy dx. I need to find dy dx. And of course, what we would love is if y were a function of x. But do we have y as a function of x? Do we have that? No. Now, of course, we could solve x squared plus y squared equals 25. We could solve that for y. We could. But there's another way to do this, and sometimes, incidentally, it's impossible to solve some equations explicitly for y. So we need a way to handle this kind of situation. We understand that since in x squared plus y squared equals 25, we understand that for every x value, there's a y value. So y is implicitly a function of x. Y is implicitly a function of x. So this approach that we're going to use, called implicit differentiation, we understand that y is implicitly a function of x. So here's what we do. We're going to use implicit differentiation to find dy dx. And I just drew a picture of the circle, a nice picture. So we have x squared plus y squared equals 25. What we do is we take the derivative with respect to x of the left side. But of course, this is an equation here. This is an equation. So if I take the derivative with respect to x of the left side, I have to take the derivative with respect to x of the right side. That's fair, right? That makes sense. Now the question is, what is this bias? Well, on the left side, we have the derivative of a sum, x squared plus y squared. We know the derivative of a sum is the sum of the derivatives. And on the right side, we know the derivative of the constant 25 equals 0. So on the left side, now you have the derivative of, well, first of all, are there any questions up to this third step here? Maybe give me a thumbs up if you're comfortable. All good, John, great. All right, Nicholas, very good. Joe and Zoe, very good, very good. All right, well, we know the derivative of x squared. We know that equals 2x. Okay, but the derivative of y squared with respect to x is going to be 2y times dy dx. We're noting that y is a function of x. Okay, it's implicitly a function of x. So the derivative of y squared with respect to x is 2y dy dx. What rule did I use here? I mean, what rule did we use? Well, the power rule was involved. That's right, Nicholas. But if it were just the power rule, I'd have 2y, 2 times y. I have here 2 times y times dy dx. Ah, that's the chain rule. That's the chain rule. Good, everybody. Good. Nicholas, Zoe, and Mitsua. Use the chain rule here. Because y is, that's right, Rodrigo. Y is a function of x. So I'm not done differentiating. I got to take the derivative. So, you know, I got 2 times y to the first power. But then I have to take the derivative of y with respect to x. Are there any questions on that step there? So this is the first power here. I mean, we know it's there, right? Okay, well now I can solve this for dy. And so I'll get dy dx equals negative 2x over 2y. And this, of course, would only work when y is not equal to 0, because I divided by 2 on like here. when I had 2y dy dx equals negative 2x, I divided both sides by 2y. And you've been taught never to divide by a variable. But you can divide by a variable so long as you put the restriction in that the variable can equal 0. And so therefore dy dx will equal negative x over y. Are there any questions up to this stage here? All right, are we ready to move on? Thank you, Chateau. Thank you, Nicholas. Are we ready to move on to the next page? John's good. All right, let's move on. Thank you, everybody. So now I'm going to evaluate dy dx when my coordinate xy is 3, 4. And that's going to be negative 3/4 because negative 3, well, 3 is my x and 4 is my y. And so therefore, the equation of the tangent line to the circle at 3, 4, you just use the point slope formula and work it out, and you'll get the equation of the tangent line. Naturally, we use the point slope form of a line, y minus y naught equals m times x minus x naught. The slope is negative 3/4, and 3, 4 is the coordinate we're using. So if you work this out, in the end, you're going to get y equals negative 3/4 x plus 25/4. And indeed, that will work very well with. I mean, that is if you draw the tangent line to the circle, you'll see that makes sense. Remember, we said that the slope would be negative of the tangent line. And the tangent line should, well, I'll go back to the picture to sort of justify it. Are there any questions? All right. All right, well, let me go back to the picture then. So, well, actually, hold on. So 3, 4. 3, 4 is roughly here. No, I got to be careful. Maybe like right here. 3. 4. Hold on. Let's make this look good. One moment. Okay, so this is coordinate 3, 4, and there's the tangent line to the circle at 3, 4. And I'll note that, maybe I'll put it here. I mean, we know, hold on. We know that right here is the value 5. So the slope, I mean, the slope is like, almost looks like -1, but it's -3/4, so that tangent line. And where it intercepts the y-axis, right there, yeah, that could be 25/4 or 6.25. Sure, that makes sense. All right, so are there any questions? We'll do another problem, but are we? All right. All right, well, let's move to another problem then. Okay. Let me give you a moment to copy this example down. Okay, so here, wow, this is a curve, an interesting curve. And you know, to plot that curve, I mean, do you think it would be easy to solve that for y? I guess it would be possible, but certainly not easy, right? Certainly not easy to solve that equation. If we wanted to isolate the y, we'd have to take the arcsine of both sides and then divide by x, and there'll be a square root involved. Then we have to take the square root of y squared, and then we got the plus or minus to worry about. I mean, man, you know, it's going to be messy solving that for y. I mean, if I wanted to do dy dx and convert this equation into y equals a function of x, that's going to be messy. So let's go ahead and use implicit differentiation. We know that y is implicitly a function of x because for every x value, there's a y value. So y is implicitly a function of x. If you substitute an x value, okay, you could solve this equation for y. So y is implicitly a function of x. Okay, so we're going to do the same procedure. We're going to take the derivative with respect to x of both sides of the equation. Okay. And on the left side, you have the derivative of a sum. Well, that's the sum of the derivatives. And on the right side, you're taking the derivative of the sine of x squared with respect to x. So what rule do you have to use? What special rule do you have to use on the right side? You have to use the chain rule to differentiate that right side. So the derivative of the so what's the outer function for this sine of xy squared? What's the outer function? The sine of x. Good. So, well, the derivative of the sine is the cosine. And then I need to take the derivative of the inner function. That's the xy squared. But you notice I don't do it all at once. Okay, I don't do it all at once. Because, you know, that you can easily make a mistake if you try to do all the work at once. So I have the derivative on the right side here of x times y squared. What rule am I going to have to use to handle that derivative? The derivative of x times y squared. It's the derivative of a, what is x times y squared? That is a what? That is a, begins with a p. That's a product. So, oh, I'm going to have to use the product rule. Good. Good, everybody. That's the product rule. Okay, so I'll do that. The left side's no problem. The derivative of 1 is 0. The derivative of x with respect to x is 1. But now I'm going to use the product rule. I'm going to use the product rule. And I have two functions. I have an x and I have a y squared. So this is my f and my g. So the derivative of the product fg is f prime g plus f times g prime. And actually, right, okay, let me just make these parentheses a little bit bigger. So when you differentiate the y squared, you get 2y times y prime. What rule did we use there to differentiate the y squared? Right, so this is 2y times y prime that's equivalent, by the way, that there is equivalent to 2y times dy dx. So it's just another way of writing dy dx as y prime. What rule did we use? All right, Ian, very good. So this is y prime. We use the power rule to get the 2y, but then we multiply 2, so you know that's 2y to the first power, right? But then we multiply that times y prime, so it's more than the power rule we used. We used the chain rule. Good. This is the chain rule. Chain rule. Good, Nicholas. Okay, and so 1 will equal the cosine of xy squared times y squared plus 2x times y prime. All right, this is the first power here. Okay, and we can solve that for y prime. This is just algebra. I'm going to get the y prime by itself by subtracting over to the left the y squared cosine xy squared. And then I'll get the y prime. And remember, y prime equals dy dx. Okay, take a moment to copy it down, make sure you're good with it. Are there any questions at all? Can you simplify out the cosine? Good question, Ian. You cannot, because you have this minus here. If we didn't have the minus there, if we didn't have the 1 and the minus there, then we could simplify out the cosine xy squared. But all right, how many think this is like maybe one of the most beautiful things they've seen in math? The implicit differentiation. How many think it's pretty cool? Yeah, Nicholas loves it. Rodrigo, I guess that's a no. Layla doesn't find math beautiful. Oh, well, maybe Layla, you know, maybe not now, but who knows? Who knows? You know, we'll see. Don't worry, Joe. We'll see. We'll try to see if Layla changes her mind later here. And I agree, John. It does help a lot to understand. So, all right, we have 15 minutes left in class. What I'd like you to do now is please stay in class session. Let's use this time for you to work on your your homework for Friday. So I have taken off the password for that. So go into WebAssign and work on your classwork for Friday. Let me put a stop on the recording here.